you deposit $15,000 into an IRA account, and the annual interest rate is 6.25% compounded monthly. And now you want to know, how long will it take for your investment to double? The first thing that we need to do with this is write our exponential growth equation for this situation. So let's work through the information that we have to start with. We have that your initial amount, A0, is equal to $15,000, the amount you put in. We also have the annual rate is 6.25%, or in the decimal form, which we prefer that to be in, we need to divide it by 100, and that gives us 0.0625. But it's compounded monthly, which means we need to take the annual rate and divide it by 12 to get our monthly rate. And now this one is not exactly a nice number. It gives us 0.00520833, and it keeps going on forever for that decimal. That means we can't round this. We need to keep this as its exact fraction in our equation that we write. So now our exponential growth equation, we have that A is equal to our starting amount of 15,000 times 1 plus our monthly rate, which is 0.0625 over 12. And now this is being raised to the t, but I want to have t in this be years and not months, so I need to multiply t by 12 in order so that they match back up. So now that I have my formula for this, I need to know, I want to find how long it will take for this investment to double. That means I need to replace my A with 2 times my starting amount and then work to solve for T. So I'm going to have A be replaced with 2 times 15,000. And now this is still equal to 15,000 times my 1 plus the 0.0625 over 12 raised to the t times 12. The nice thing with these problems when we're asked for how long it will take for it to double is that our starting amount doesn't actually matter, because if you notice here, they're just going to cancel out. I need to divide by 15,000 on the right side to get rid of that there. And when I divide by the 15,000 on the left side, they're both there to just cancel out with this. So whatever you have for your starting amount, it should just end up canceling out anyway, and it doesn't actually matter. So now this is going to give us the equation 2 is equal to 1 plus 0.0625 over 12 raised to the t times 12. And now our goal with this is to solve for t. T is in the exponent, which means we need to introduce logarithms. So we're going to use our 1-to-1 property to take the log of both sides of the equation. So we can rewrite this as being log of 2 is equal to log of everything that we have on that right side of the equation, which is 1 plus the 0.0625 over 12 raised to the t times 12. And now we have our t, the t times 12, it's the exponent inside of the logarithm, which means we can use the power property to bring that t times 12 out to the front of the logarithm that it's in. So my left side of the equation is going to remain unchanged, log of 2. But the right side, I'm going to take that t times 12 and move it to the front of the logarithm. So we have t times 12 times our log of what we have left in the logarithm, which is 1 plus the 0.0625 over 12. And now we want to solve for t. T is being multiplied by this 12 log of the 1 plus 0.0625 over 12. So we can just divide all of that to the other side of the equation. So now this is going to give us, to cancel all of that out on the right side, we're only left with t over there. So we have that t is now equal to log of 2 over 12 log of 1 plus the 0.0625 over 12. And now before you go to put this into your calculator, we can put this into our scientific calculator almost directly like this. The only thing that we need to add is a set of parentheses around that denominator there. Otherwise, it won't include that entire piece in the denominator of this fraction. So now we can input this into our calculator, and you should then get that t is going to be equal to about 11.12 for a value. And here I have wrote my equation, my exponential growth equation for t to be in years. So this would be 11.12 years for how long it would take for their $15,000 to become double that amount, $30,000.